just reading the CV, of course, did his PhD at Strasbourg Observatory in France. And it was there that he obtained the best PhD thesis in 2018. So that's a great acknowledgement of his thesis work. Since finishing there in 2018, he's been working as a postdoc at the Department of Physics in Stockholm University. But he's soon off to the Max Planck Institute in Heidelberg on an Alexander von Humboldt Fellowship. So, well done and welcome. Welcome to Centre for Astrophysics at Swinburne. And over to you, Khyati. You want to share your screen?
Yes. Could you see my slides and also hear me well?
Yes, that looks great.
Perfect. Hello, everyone. It's a real pleasure to be talking to you today. I wish I was there with you in person, but it's still a nice way to be linked to all of you through Zoom. Broadly speaking, today's talk is about understanding the formation of the Milky Way halo. But in doing so, I'll also be making a case of the LMS1 stream, which is a stellar stream of the recently discovered stellar stream of the Milky Way, as I think it's a very interesting fossil remnant that gives us the information about the early formation of our galaxy. And this map that I'm showing you here is a map that we recently constructed using the Gaia Early Data Release 3 and the Stream Finder algorithm. So all the stars that you're seeing here are basically Gaia stars that are color coded according to the heliocentric distances. So the blue stars here, or the blue streams, are closer to us. The redder stars are further out into the halo. So the LMS1 stream that I'll be talking about eventually is not shown here yet, but this is just a map that I thought of sharing with all of you. So the outline of today's talk will be that I'll share with you what's our basic motivation to understand the formation of the Milky Way galaxy, and then how do tidal stellar streams help us unravel the mystery of the formation of the Milky Way halo. So how we can use them to understand how the halo population of the Milky Way formed or was born. Then I'll move on to the detection and the analysis of the stellar stream using my Stream Finder algorithm that I constructed during my PhD, and I'll be talking about Stream Finder a bit. And this stream was detected in the Gaia Early Data Release 3, so I'll be talking about this as well. And then finally, one of the most interesting things about the talk will be that how the characterization of the LMS1 stream advances our knowledge about the formation of the Milky Way halo. So what this particular stream itself is telling us about the Milky Way halo formation. And then finally, I'll summarize these results. So I know there are lots of people working in different domains, in stars, in cosmology, or in astrophysics. But one of the basic questions that I believe that many members in the audience would be interested to understand is that how do galactic halos form in our universe that is dominated by dark matter? And this is, of course, an interesting question, both from the perspective of understanding the galaxy formation and also from the perspective of understanding dark matter. Because as per lambda CDM, we know the dark matter is the major cosmic driver of the universe that leads the formation of the galaxies. And also, these simulations tell us that the formation of a galaxy is not a one-step process where a dark matter just condenses to form a big halo. It's a multi-step process, and by multi-step I means that the formation of a galaxy is an ongoing process where multiple accretions of smaller galaxies or subhalos take place, and these as you can see in this video, these multiple smaller galaxies or subhalo keep on merging with the host halo, and they populate the halo of that galaxy. And we also have from the simulations this temporal information that at very high redshifts, at very earlier times, there was an active phase of merging where where the rate of accretion of these smaller galaxies was much higher compared to the recent times, compared to last 6 to 8 gigayears, where only 2 to 3 mergers would have occurred, at least for a Milky Way like galaxy. So this basic understanding that we are obtaining is coming from simulations, but in principle, when we try to connect the observed galaxies with this prediction of the hierarchical growth of dark matter halos from simulation, So the connection between this observation and theoretical prediction, it's a bit challenging, it's a bit hard. And this is primarily because what we observe for the present day, so here I'm showing you a, a sketch of a Milky Way-like galaxy, where when we try to observe a Milky Way-like galaxy, what we see are basically these star components, because of course we cannot see dark matter. What we see are only stars and also gases. So what we see is that there's a host galaxy that is sitting in the center, which is surrounded by a halo that comprises of dark matter and also stars, but the population is too sparse, sometimes to be clearly visible or to be resolvable by telescopes. And then we have these dwarf galaxies, or these smaller galaxies surrounding the main component of the host galaxy. But what lambda CDM is telling us is that the real picture is something like this, where there are these abundant of galaxies or smaller subhalos that are just accreting and merging onto the host halo. So we want to connect these two pictures together, or these two understandings from observations and theory together to unify the understanding of galaxy formation. So stellar streams in this context are quite useful to unravel the mystery of halo formation, if you will. So what lambda CDM model is telling us that a majority of stars or even dark matter that we observe in a halo of any given galaxy, or at least a Milky Way mass galaxy, is a result of the accretion of several smaller galaxies or dwarf galaxies, as you can see in this video here. So these infalling dwarf galaxies basically get tidally stripped and disrupted by the galactic potential of the host, and then they end up forming these stellar streams. And it is precisely due to this reason that merely the observation of stellar streams in any galaxy provides a testimony of the hierarchical growth of history of hierarchical growth history of the halos. Because if you just observe these stellar streams, that is basically telling us that all of these stars that you observe in a stream were an ex-situ population that were accreted in the halo from that external dwarf galaxy. And this is the reason that stellar streams provide an excellent opportunity to examine this hierarchical formation scenario of Milky Way mass galaxies. Now I'll briefly just dedicate a slide on stellar streams, that what are these structures. So the idea is that you have a progenitor galaxy, a progenitor system that accretes, that merges with the Milky Way, and its stars get tidally stripped by the underlying galactic potential, and then it forms this elongated stream of stars. But the most interesting thing about stellar stream is that stars that escape the potential well of the progenitor, they end up closely delineating orbits along the progenitor system as well. So at a very crude approximation, stellar streams closely delineate orbits. And this is precisely this orbital information that stellar streams provide, is that they are very powerful probes of the hierarchical formation of the halos, of the distribution of dark matter, to probe alternate theories of gravity, because this orbital information also contains information about the gravity. So by alternate theories of gravity, of course, I mean Mond and other theories of gravity, the figure rotation of the halo, and many more, the many more uses of the streams that you can see here. But of course, I don't want to digress. Our focus of the presentation of this talk will be to understand that how do stellar streams serve as a really nice probe of the hierarchical formation history of the halo. And one of the reasons, of course, is because we can use the orbital information of stellar streams that you can see here to trace these streams backward in time to be able to reconstruct the accretion history of that galaxy. So that is why stellar streams are quite powerful, because they come with this orbit information which can be traced backward and forward in time. And these stellar streams, although we do observe them in simulations, as I showed you here in lambda CDM simulations, but we've also observed them through various surveys. So here is our nearest galaxy, Andromeda, as mapped by the PANDA survey, and you can see this giant stellar stream surrounding the Andromeda galaxy, which again suggests that okay, at least some part of the halo of the Andromeda, if not all of it, was made by the accretion of some dwarf galaxy that merged with Andromeda. And then you can see several other tiny stellar streams as well, the stream of M33 galaxy as well. And this is the case of Andromeda. Then there are several external galaxies as well, around which you can see these streams surrounding these halos. So we have quite lots of evidence of the fact that indeed Milky Way mass galaxies undergo this hierarchical formation process, and that is how the halos form. And of course, we have also observed since the beginning of 2000, last decade, last to last decade rather, that even the Milky Way has these stellar streams. So one of the exemplary cases is the Sagittarius stream that I believe many people are aware of in the audience. And so this is from the SDSS map in 2006, 2007. This is from 2018 Dark Energy Survey map, where several other streams were also observed. So this mapping of the stream is sufficient to make a case that the Milky Way halo is in fact a result of the hierarchical formation process as predicted by lambda CDM models. But the thing is that these photometric surveys such as SDSS, Dark Energy Survey, or PAN-STARRS, they do not provide velocities, which means that although we can make a case that Milky Way had an accretion history, but we cannot really understand or model these accretion events to understand that how did the Milky Way halo actually form, because we do not have velocity, so we cannot trace the orbits of these streams backward in time, for instance. But of course, we know that we have maximum amount of information for our own Milky Way, so we can best answer this question for the Milky Way itself, and especially because of Gaia, because with Gaia, we now have velocities for many stars in our galaxy. And with this velocity information, we can perhaps also try to understand the chronological accretion history of the Milky Way. So not just the number of accretions that took place, but also in which sequence in time that those accretion events took place. And this beautiful picture that you're seeing here is basically a Swinburne astronomy production that you can see here. And I stumbled upon this picture while reading an article. I'm sure many members in the audience are aware of this. So I could not resist to not use this picture in the presentation. So are there any doubts until now? Because then I'll be slightly shifting the topic and moving to the streams. What do the streams of the Milky Way inform us? If there are no questions, then I'll just proceed with it.
Yeah, I don't see any questions. Just carry on.
Okay.
That's fine. Yeah.
Perfect. So yes. So first, so let me try and explain what are the sort of informations that we want to extract out of streams, or rather, what are the known dwarf galaxy streams of the Milky Way inform us generally? Just what are the sort of information we want to understand from streams? So in the Milky Way itself, we know of about 4 to 5 dwarf galaxy streams. So streams formed by dwarf galaxies. Two of the prominent examples are the Sagittarius stream and the Cetus stream. And for example, what Sagittarius stream tells us is that its dynamical and chemical models indicate that this accretion took place 3 to 6 giga-year ago. So we know that from the perspective of Milky Way formation, Milky Way halo formation, we know that there was an accretion that took place sometime between 3 to 6 giga-years ago. We also know that Sagittarius brought in a population of about 8 to 10 globular clusters out of 160 globular clusters that we observe in the Milky Way. And this we know both on the basis of chemistry and also on the basis of comparing the orbits of these globular clusters with the stream of Sagittarius that you can see here. So all the globular clusters that have orbits very similar to Sagittarius would imply that they were accreted within the parent galaxy of Sagittarius. And we know that the parent galaxy of Sagittarius has a mass of about 10 to 9 to 10 solar masses, and the stellar mass is 10 raised to the 6 to 7 solar masses, which means that whatever the mass of the stellar halo is, which is close to 10 to the 10 solar masses, at least 10 to 6 to 7 stellar mass in the halo was contributed by the Sagittarius dwarf galaxy. So this is the sort of basic information that we can try extracting out of streams when we detect and analyze it. Similarly, for the Cetus stream, the dynamical models tell us that the accretion took place about 5 giga-years ago. Cetus brought in at least one globular cluster, that is HGC 5824. The parent galaxy had a halo mass of 10 to the 9 solar masses, stellar mass of 10 to the 5 solar masses. So this is also quite informative. But the thing is that all of these streams, all of these dwarf galaxy streams that we know of in the Milky Way till date are dynamically young systems, which means that these streams were only accreted 3 to 6 gigayears ago. One of the reasons that we also think so is because these streams are quite coherent in phase space. So Sagittarius and Cetus are quite coherent in phase space, which means that they did not have enough time to phase mix, which means that they were only recently accreted. So a question to think about at this stage is that at present day in the Milky Way, does our galaxy contain signatures of dynamically old streams, those streams that were accreted 8 to 10 gigayears ago, for example? And this is an interesting question because even the lambda CDM model suggests that, as you remember, that the rate of accretions were quite higher at earlier times. So there were lots and lots of accretion happening in the early history of our galaxy. So we do expect lots of streams to be found. But is it that those streams would have been completely phase mixed and they're hard to detect? Or is it that just we just need a better toolkit to be able to find those streams? And also to understand the full chronological history of the Milky Way halo formation, we should be able to combine these dynamically young streams, these dynamically young systems with the dynamically old systems to be able to unravel the full chronological history of the halo. So that is our motivation to try and understand those dynamically old streams. Right, so of course, one of the best ways to detect those streams in the Gaia dataset. So I'll just talk a bit about Gaia survey now. So Gaia is measuring 60 phase space position of stars. It measures positions, proper motions, which are basically angular velocity, parallaxes, which can be dubbed as distances, and also the photometry and radial velocities as well. So the first data release was in 2016. The second one was in 2018, and the latest data release was in 3rd December 2020. So that was Gaia early DR3. So Gaia EDR3 provided 5D astrometry for about 1.8 billion sources. So by 5D astrometry, I mean it provided 2D positions, 2D proper motions, 2 components of angular velocities, and one-dimensional information in parallaxes. So that was just 5D phase space information. And it also provided additional radial velocities, but for only about 7 million stars. So that's quite a small fraction of stars for which we have complete 60 phase space information in the Gaia dataset. So here I'm highlighting this circle. So this is just a sketch, just to make this point clear that that Gaia EDR3 5D astrometry is providing information for a majority of stars in the galaxy, but the 60 information is only present for very tiny stars, brighter stars around the sun and also around the bulge, for example. So using this 60 phase space information, it's quite easy to detect streams, to find streams, because what you can do is that you can simply compute the energy and angular momentum of all the stars, because you have 60 phase space information. And then you can look for clumps in this energy angular momentum space, because remember, stellar streams closely delineate orbits. And in an axis symmetric potential, orbits, the energies and angular momentum of orbits are conserved, they're constant. So you can find these clumps of stars, and then you can regard them as streams, basically. But with this procedure, this very simple procedure of finding streams, you can only find nearby streams, because note that the 60 information is only present for very nearby brighter stars that have magnitude less than 12 or so. But over 99% of stars in Gaia EDR3 do not have radial velocities. So we cannot do this energy angular momentum plotting for more than 99% of the stars for Gaia EDR3 sources. This means that in order to find halo streams, in order to find streams that are very distant from us, we need a dedicated toolkit to do such searching. So we need to build a search algorithm to find streams. And with that motivation, I had started my PhD back in 2016 at Strasbourg to basically build an automated algorithm that can detect streams in the Gaia dataset, keeping in mind that Gaia will not have radial velocities for a majority of halo stars. So just to quickly review what StreamFinder is doing is that StreamFinder uses Gaia's 5D phase space measurements for a given star. What StreamFinder does is that it uses the phase space information of that star and it integrates an orbit, right? But in doing so, because a star does not have radial velocity, it samples over the orbit. So for a given star, we end up sampling over 10,000 orbits or so. And if the star that you're analyzing is a stream star, and if you hit upon the right radial velocity, then the orbit will see you through the remaining stream member, will see you through the remaining star members of that stream, and in that case, the star will get a higher likelihood value. But for example, if you're analyzing, if you were repeating this procedure with a contaminant with a typical halo star that is not part of stream, then the integrated orbit will not pass through the any other star, and this star will get a very low likelihood value. So in this way, a stream star will get a high likelihood value, a contaminant will get a low likelihood value, and you can assign these likelihood value to all the stars and create a likelihood map in this way. I know it's a bit complex procedure, but it's basically at its heart, Stream Finder is basically integrating orbits to find streams. Um, and so the model parameters are positions, proper motions, parallaxes, and also photometry, because in finding streams, we ensure that the detected stream follows a certain stellar population as we expect from dwarf galaxies, for instance. And because stream detection is also a signal detection at the end of the day, so it's all about trying to detect a signal, sometimes even a very weak signal, on top of a contamination. So this is how the entire stream finder algorithm can be expressed in this likelihood function, where the first term is the model, is the signal term that takes care of the length of the stream, that because stream finder asks you the length of the stream you're interested to find, the width of the stream. So if you want to find a wider stream, the width will be wider, 500 parsec, 1 kiloparsec, depending on what stream you want to find. If you want to find a globular cluster stream, then the width will be smaller, 50 parsec, 20 parsec or so. Then there's luminosity function term and the color term to take care of the stellar population, the proper motion term, and parallax term. And then we also build a contamination model to take care of the contamination, because we're interested to find a weak stream signal on top of the contamination of the halo. So this is how Stream Finder works. And here, uh, this is one of the maps of the Stream Finder that we recently produced using Gaia EDR3. So here, all the stars that you're seeing are Gaia sources, color-coded according to the proper motion in the latitude direction. So the color coding basically tells you that these detected streams are coherent and also in the velocity space. So you can see lots and lots of streams in this map. Just to highlight some of the interesting streams is the stream Silger, which is quite metal poor system. It has a metallicity of minus 2.92, which is quite low. Then there's stream of the famous Omega Cent Omega Cent star cluster that you can see here. There's very famous GD1 stream that is quite useful to understand the dark matter distribution in the Milky Way. Many people have analyzed this stream for the purpose of probing dark matter, myself included. You can also see many globular cluster streams from NGC 288, from M5, M92, and so on. And there's recently we also discovered a new stream that seems to have a metallicity, very low metallicity of minus 3.4. So I wouldn't say much about the stream because one of our team members is writing a paper on it right now, which hopefully will be out soon. But it's nice to see that we have all of these streams that we have started to analyze now. And also I should say that most of these streams are globular cluster streams because they're quite narrow, as you can see, and many are not dwarf galaxy streams that I'll now be focusing upon. So now I'm moving towards the last topic of the presentation, the detection of the LMS1 stream using Gaia EDR3. And here's the paper that I'm highlighting. So the remainder of the talk, we'll try and focus on what is the nature of LMS1 stream, because I'll be making this case. So in the remainder of the talk, we'll try and do two things. One is that we'll try and understand the LMS1 stream itself. We'll do its chemodynamical analysis. But by analyzing LMS1, of course, our broader question is to understand how the knowledge of LMS1 helps us understand the formation of the Milky Way halo itself. So these are the two topics that I'll request you to keep in mind as we proceed in the presentation. We want to understand LMS1, but we also want to use LMS1 to understand the formation of the Milky Way. Right. So this is the processed map from Gaia EDR3 using Stream Finder, as you can see here. The top, all the sources are Gaia sources again. The top panel is color-coded as per the proper motion along longitude direction. The bottom plot is color-coded according to the proper motion in the latitude direction. And you can see lots of features here. You can see the previously known orphan stream. You can see part of the Sagittarius stream here. You can see the gas structure. Maybe some of the audience members are familiar with this. But one of the most striking features that we detected was the LMS1 stream that you can see here. The stream you can see in both the maps. So LMS1 was detected as one of the most striking features in Gaia EDR3. It has a width of about 750 parsec, so the width perpendicular to the stream, and it lies at a heliocentric distance of about 20 kiloparsec. It is a very metal poor structure, so minus 2.1 metallicity, and has a significant metallicity dispersion. And these things basically suggest that LMS1 is indeed a remnant of a dwarf galaxy and not a globular cluster, for example. So it's a stream produced from a dwarf galaxy. But of course, we do not know the dwarf galaxy of this stream because perhaps it has been completely disrupted. So we do not find any O-dense clump along the orbit of LMS1. This stellar mass of LMS1, this metallicity of LMS1 implies that its parent galaxy had a mass of about 10 to the 5 solar masses or so. So the parent galaxy was probably much like the Draco dwarf galaxy that we present today. You can also see some of the other features associated with LMS1 that we dubbed as sub-1, sub-2, sub-3. You can also see this southern agglomeration of stars that, and all of these, and this curve that I'm showing here is basically the orbit of LMS1. And you can see that parts of this orbit also passes through sub-3, sub-2, sub-1, and also through the southern agglomeration of stars. And this basically implies that these sub-3, sub-2, sub-1 are probably multiple wraps of LMS1 that you can see here. And also the southern part of LMS1 additionally supports this idea that perhaps the entire LMS1 stream is wrapped around the inner Milky Way halo, is wrapped around the inner 15 to 20 kiloparsec of the inner Milky Way halo. The reason that there's gap over here that you can observe is because we do not process this low latitude region of the sky because there are lots and lots of stars, and then the stream finder computation will become very expensive. So we cut out only those regions that are above and below 20 degrees in latitude. Then we try to constrain the orbit of LMS1. With Gaia, we have the 5D astrometry. So I cross-match these Gaia sources of LMS1 with the spectroscopic surveys of SDSS, Lamoste, and Apogee to get the missing radial velocities. So with this cross-match, we now have the complete 60 phase space information. And with this 60 phase space information, we can now try to constrain the orbit of LMS1. So this orbit is shown here. And some of the orbital properties of this orbit are its eccentricity 0.2, which means the orbit is nearly circular. It's a prograde orbit because the z component of angular momentum is negative, quite negative, minus 700 kiloparsec kilometer per second. So LMS1 has a prograde motion. Its pericenter is 10 kiloparsec and its epicenter is only 16 kiloparsec. The reason for highlighting these two orbital properties is that none of the known dwarf galaxy streams or even intact dwarf galaxies have such low eccentricity. So for example, most of the streams in dwarf galaxies have quite high eccentricities of more than 0.5, 0.6, which means they're on very radial orbit, but LMS1 is not, it's on a circular orbit. Also, most of the streams and intact dwarf galaxies have very large epicenters of more than 35 to 40 kiloparsec. But the epicenter of LMS1 is very low. It's only 16 kiloparsec, so it's within the 20 kiloparsec radius. So these distinguishing orbital properties make LMS1 a very interesting dwarf galaxy stream. And we can then attempt to understand what could be causing such strange and intriguing orbital properties of LMS1 is that maybe the LMS1's orbit got circularized, which is possible if the parent galaxy of LMS1 was very massive and it underwent a dynamical friction, and the dynamical friction circularized the orbit of LMS1. The reason of its low epicenter could be that if LMS1 accreted very early in time, about 8 to 10 gigayears ago, then it would naturally be confined to the very central regions of the Milky Way. And that is because Milky Way mass galaxies, we know, grow inside out, which means that the early accretions would be confined to the very central regions, and the accretions that occurred later on would be confined to the outer halos. For instance, the Sagittarius stream that I showed before is confined sort of to the outer regions of the halo because it's a recent accretion, but LMS1 must have accreted early in time because it's confined to the very central regions. So we can use this orbital property of streams to say something about when the accretion would have taken place. Um, then we can play a slightly different game. What we can do is compare the orbits of LMS1 and the globular clusters of the Milky Way, and then see that which all globular clusters have their orbits sort of similar to the orbit of LMS1, which would mean that these globular clusters must have been accreted within the parent galaxy of LMS1. So here I'm comparing the orbit of LMS1 in black with the orbits of two globular clusters, NGC 5024 and 5053. And as you can see that these globular clusters, the orbits of these globular clusters are consistent with the distribution of data points of LMS1 that you can see here. Particularly interesting is the case of NGC 5053, whose orbits practically traces the orbit of LMS1, so which is quite interesting. Also, as a side check, we also compared the metallicity of these two globular clusters with the metallicity distribution function of LMS1. And you can see that the metallicity of these two globular clusters matches with that of LMS1. I'll discuss PAL5 and INDUS in the subsequent slides. So this was also an interesting test to see that which all globular clusters were accreted inside the LMS1 parent galaxy. Finally, so the overlap of these two globular clusters with LMS1 served as a motivation for us to go crazy and then try and compare the properties of LMS1 with all the globular clusters of the Milky Way and most of the streams in the Milky Way and compare them in the dynamical space. So here I'm showing you two example maps, the projected action map and the energy angular momentum map. And the idea is that systems or stars that are very closely clustered in these maps must have accreted within the same parent galaxy. And the reason for that is that we know that the energy is conserved for an axisymmetric in an axisymmetric potential, which means that the objects that would have accreted inside the same parent galaxy must have more or less similar energy because they were accreted inside very similar orbits. So that's fine. And we also know that the actions are adiabatic invariants, so even they would be conserved for a slowly evolving potential, especially if it's an axisymmetric potential. So these actions, and so anything, all the stars and objects that are sort of closely clustered in the energy action space basically imply that they must have accreted inside the same parent galaxy. So this is also one of the ways of trying to associate different objects with the same accretion event, generally speaking. Right, so now I'll flash some of the data points, the globular clusters of the Milky Way and the LMS1 stream as well, and we'll see that they cluster together, which all globular clusters cluster with the LMS1 objects. Right, so here is the same map. Here, the gray stars show you all the globular clusters of the Milky Way. The blue points show you the LMS1 simulation based on the best fit orbit of LMS1. And then you can see these three globular clusters, 5053, 5024, and PAL5, that strongly overlap with the LMS1 in the projected action space and also in the energy angular momentum space. You can also see another stream in this, which was one of the few streams that we tried, whose orbits we integrated and compared with LMS1. And even the Indus stream overlaps with LMS1 in this dynamical action energy space. And then we also compared other orbital properties of these objects that can also be done as a side check to ensure that overall the orbits of these different systems compare well with that of LMS1. So this overlap of so this was just an evidence of the in the dynamical space. What we can do is also try and compare the stellar population and the metallicity of these different objects of these different globular clusters and Indus with LMS1 and see how they compare in the metallicity space and also in the color magnitude space. So you can see that these four objects, Indus and the three globular clusters, uh, overlap with the metallicity distribution function of LMS1, and particularly the CMDs of Indus and 5024 and 5053 match quite well with the CMD of LMS1 that you can see here. So this means that at least NGC 5024 and 5053 and Indus were accreted inside LMS1 parent galaxy because they strongly overlap in this dynamical chemistry and stellar population space, which means that these objects and stars were formed inside the same potential belt. So they had sort of similar sort of chemical enrichment and also star formation history. Um, so now I'm moving towards the conclusion of my slide. So then what we can do is that we can, along with LMS1, we can put these other two dwarf galaxy streams in some perspective. So here I'm comparing the Sagittarius dwarf galaxy stream, the Cetus stream, and the LMS1 stream. And based on these streams, you can try and understand that together, what are they telling us about the formation of the Milky Way halo. So just to quickly go over their properties. So Sagittarius is a polar dwarf galaxy stream. So all of these, so first of all of these three are polar dwarf galaxy streams. So by polar, I mean that their orbits are inclined almost perpendicular to the plane of the galaxy, to the disk of the galaxy. So for instance, Sagittarius, so an inclination of 90 degrees would be perfectly perpendicular to the galactic disk, but Sagittarius has an inclination of 76 degrees. Cetus 60 degrees and LMS1 75 degrees. Sagittarius spans the outer galactic halo with a galactocentric radius of 15 to 100 kiloparsec. It has a wide range in metallicity. It contributed at least 8 to 10 globular clusters to the Milky Way, and it's relatively a dynamically young system that was only recently accreted. Right, that's the understanding of Sagittarius. Cetus spans, on the other hand, spans the intermediate galactic halo, so between ranges from 24 to 36 kiloparsec. It has a quite low metal poor structure. It contributed at least one globular cluster, 5824. LMS1 spans the inner galactic halo, 10 to 20 kiloparsec. It's quite metal poor. It contributed at least two globular clusters plus one stream to the Milky Way. And it's a dynamically old system that was likely accreted 8 to 10 gigayears ago. So one of the things that I'm trying to understand, and it will be nice to also have finally have some opinion from the audience that what they think of, is that I'm trying to understand that can these streams, these observation of these streams, be put in some chronological perspective, in the sense that because we know that the Milky Way like galaxies, Milky Way mass galaxies form inside out, have an inside out growth. Is it really that the LMS1 stream accreted early in time, and that's why it's surrounding the inner Milky Way halo, followed by Cetus that was accreted later on, and hence surrounding the intermediate halo. And then finally, the Sagittarius dwarf galaxy came in and populated the outer, mostly the outer regions of the halo. Can we dub these observations and put them in some chronological perspective to build, to understand the formation of the Milky Way halo? But this is something that I'm trying to understand right now at a personal level. The next question that we can ask based on the observations of these three dwarf galaxy streams is that how common are such polar dwarf galaxy streams in Milky Way mass galaxies as per cosmological simulations? And the motivation behind this question is that if such polar dwarf galaxy streams are common, then is it that polar streams are really the major source of stellar population in Milky Way mass galaxies? Because note that having three dwarf galaxies in a quite polar configuration is a bit unique. This is something that at least I personally didn't expect, that we have three or probably even a bit more polar dwarf galaxy streams in the Milky Way, and we do not really observe it in other galaxies as well. So are they common? And if cosmological simulations tell us that these polar dwarf galaxy streams are a rare event, they are uncommon, then is it that our Milky Way galaxy is a special galaxy in some way that supports this polar, either attracts the satellite galaxies to have such polar configuration, or supports this polar configuration? The potential is such that it probably makes or precesses the orbit of the stream, so that they can have this polar configuration. So this is again a sort of question. I'm not sure what merit these questions hold, but something that I'm just trying to understand right now. So with this, I hope I haven't crossed the time, but with this, I'll just quickly summarize the key points that I wanted to get across, and I hope that I have. Is that stellar streams are quite interesting structures because they provide direct evidence of the hierarchical formation of the Milky Way halo. So you just observe a stream, and that's enough. That's basically telling you that the Milky Way halo is a result of hierarchical formation. And in principle, we can simply count the number of dwarf galaxy streams, and that can eventually put a lower limit on the number of accretions that took place in the halo and populated the halo, for example. So we can do quite interesting things with stellar streams in that sense. LMS1 is also an interesting stellar stream. It has a very unique orbit. Its orbit is polar, low eccentricity, low epicenter, which basically suggests that the LMS1 accreted quite early in time, 8 to 10 gigayears ago, roughly speaking. The dark matter halo mass of parent galaxy was probably 10 to the 9 to 10 solar masses. The stellar mass was 10 to the 5 to 6 solar masses. It brought in at least 2 globular clusters, 5024, 5053, and also the Indus stream. It possibly also brought in Palomar 5, but that's something that I'm not particularly sure of because Pal 5 has a slightly higher metallicity. It sits on the higher metallicity end of LMS1, and its orbit is slightly different. Its orbital pole is approximately 140 degrees away from the orbital pole of LMS1. So although it overlaps in the dynamical space, but I'm at least not quite sure of the association, but it's interesting that it overlaps in the action space. Also, we found evidence that LMS1 is completely wrapped around the inner galactic halo. So it's quite interesting structure and would be very interesting to model it in more detail in future. And all of these properties of LMS1 seem to make it a very interesting fossil remnant of the early formation of our galaxy. And with that, I'll thank you very much for your attention.
Thanks, Khyati. That was great. Excellent talk. Very interesting.